Rechargeable batteries are embedded in everyday household environments in ways that often go unnoticed. They power cordless drills stored in garages, electric toothbrushes placed beside bathroom sinks, laptops resting on desks, cameras kept in drawers, portable speakers used in living rooms, and backup power units positioned in utility spaces. In many homes, rechargeable batteries are distributed across multiple rooms, functioning as quiet components within daily routines. Over the past 2 decades, the number of battery-powered consumer devices has increased significantly. As a result, reliance on rechargeable systems has expanded beyond convenience and into infrastructure. Households now depend on rechargeable battery packs for work tools, communication devices, emergency lighting, home automation systems, and in some cases, renewable energy storage. Even small rechargeable cells such as AA and AAA units support remote controls, wireless accessories, and sensor-based equipment. Within sustainable home energy discussions, attention is often directed toward renewable generation technologies such as solar panels or small wind turbines. However, the storage and maintenance of energy, particularly in the form of rechargeable batteries, represents an equally relevant aspect of household energy management. Batteries act as storage nodes within the broader energy ecosystem of the home. Over time, rechargeable batteries experience performance decline. This decline may appear as reduced runtime, slower charging, increased heat generation, or inconsistent output. These patterns occur across different battery chemistries, including nickel metal hydride, lithium-ion, and lead-acid systems. While degradation is a natural outcome of electrochemical processes, the pace and pattern of decline vary depending on usage cycles, charging habits, environmental conditions, and manufacturing design. As devices age, households face recurring decisions regarding what to do with batteries that no longer perform at expected levels. In many cases, reduced capacity leads to replacement. In other cases, batteries are stored in drawers or discarded in recycling bins. This cycle of use, decline, and replacement forms a recurring pattern within domestic environments. From a sustainability perspective, rechargeable batteries represent both resource investment and material waste potential. The metals, electrolytes, and structural components required to manufacture batteries involve energy-intensive extraction and processing. Extending usable life, where technically appropriate, becomes part of broader resource management discussions. Reuse strategies for common rechargeable batteries emerge within this context. Rather than immediately discarding or replacing declining units, some households and technical communities explore approaches that examine whether partial restoration, maintenance, or alternative application may be possible. These strategies exist not as universal solutions, but as components within ongoing conversations about lifecycle awareness and energy stewardship. When rechargeable batteries begin to lose capacity or show signs of inconsistent performance, households typically follow established patterns. The most common response is direct replacement. Laptop batteries are replaced through authorized service providers. Cordless tool battery packs are exchanged for new manufacturer-approved units. Rechargeable AA and AAA batteries are discarded and substituted with fresh cells. This approach prioritizes predictability and convenience. It requires minimal technical engagement and aligns with standard consumer practices. A second common approach involves basic maintenance routines. Users may attempt full discharge and recharge cycles in an effort to recalibrate battery management systems. Some may use specialized chargers that claim to refresh nickel-based batteries by cycling them through controlled charge and discharge phases. In the case of lead-acid batteries used in backup systems or small renewable installations, homeowners may check electrolyte levels, clean terminals, and monitor charging patterns. Another common strategy is limited repurposing. Batteries that no longer perform adequately in high-demand devices may be reassigned to lower-demand applications. For example, a rechargeable battery pack that no longer powers a drill effectively may still function in a flashlight or low-drain device. Similarly, rechargeable AA batteries with reduced capacity may be used in remote controls rather than digital cameras. In renewable energy contexts, households with battery banks may rely on charge controllers to manage cycling patterns and equalization settings. Automated system monitoring may adjust charging voltage or perform balancing routines intended to maintain performance across multiple cells. Online forums and user communities also document informal techniques for attempting revival. These may include slow charging protocols, pulse charging devices, or temporary voltage stimulation methods. While these approaches vary widely in technical accuracy, they reflect ongoing attempts by individuals to extend battery lifespan. These methods represent the most accessible and widely practiced responses to declining rechargeable battery performance within household environments. While common approaches may address surface-level symptoms, they often encounter structural limitations rooted in battery chemistry and design. Rechargeable batteries degrade through electrochemical mechanisms that are not always reversible. In lithium-ion systems, capacity loss may result from electrode wear, electrolyte breakdown, or internal resistance changes. In nickel-based batteries, memory effects or crystalline formation may reduce effective capacity. In lead-acid systems, sulfation can harden and restrict active material surface area. These processes are influenced by heat, charge rate, depth of discharge, and aging. Basic recalibration cycles or refresh routines may temporarily stabilize performance metrics, but they do not fundamentally reverse internal structural wear. Similarly, repurposing batteries into lower-demand devices does not halt chemical degradation. It merely adjusts expectations of output. Modern battery design further complicates intervention. Many rechargeable battery packs are sealed units with integrated management systems. Lithium-ion batteries often include protective circuitry that restricts user access to individual cells. Tool battery packs are typically encased in molded housings that limit direct servicing. This structural enclosure reduces the practicality of manual maintenance beyond external cleaning or charging adjustments. Safety constraints also play a significant role. Rechargeable batteries can present risks if improperly handled. Lithium-ion units may overheat under certain conditions. Lead-acid batteries contain corrosive electrolytes. Short circuits or overcharging can create hazardous situations. These considerations often discourage experimental reuse strategies within general household settings. Additionally, replacement remains economically straightforward in many cases. Retail availability of new battery packs, combined with declining manufacturing costs for certain chemistries, reinforces replacement as the default option. As a result, even when households are aware of sustainability considerations, structural limitations frequently constrain the scope of feasible reuse strategies. Within sustainable and energy-related fields, alternative perspectives approach rechargeable battery reuse through a broader lifecycle framework. One perspective emphasizes resource circularity. Instead of framing batteries as single-use consumables, this approach examines maintenance, reconditioning, and repurposing as potential components of extended service life. The focus is not necessarily on full restoration of original capacity, but on evaluating whether certain types of degradation can be mitigated within defined parameters. In off-grid environments and remote installations, battery maintenance skills often hold practical importance. Access to immediate replacement may be limited, encouraging users to understand battery behavior more closely. This context fosters familiarity with charging profiles, temperature management, and inspection routines. Technical communities also explore controlled reconditioning techniques specific to certain battery chemistries. For example, desulfation devices are sometimes used with lead-acid batteries under regulated conditions. Balancing procedures may be applied to multi-cell battery packs to equalize voltage across cells. In some cases, laboratory-level diagnostics assess internal resistance and capacity retention. Educational discussions increasingly frame battery literacy as part of overall energy literacy. Homeowners who install renewable systems often learn about inverter sizing and load management. Extending this knowledge to battery maintenance represents a logical progression in system awareness. Another alternative framing examines secondary use pathways. Batteries that no longer meet performance thresholds for primary applications may serve in backup or experimental roles. For instance, partially degraded cells may be integrated into low-demand systems or used for educational experimentation under controlled conditions. It is important to note that alternative perspectives do not position reuse strategies as universally applicable or guaranteed. Instead, they situate them within a spectrum of possibilities shaped by chemistry, design, and context. Within discussions about battery reuse and maintenance, structured instructional materials have emerged that focus on organized reconditioning procedures. One such resource is the new Battery Reconditioning course, which is presented as a step-by-step instructional format addressing various types of rechargeable batteries. The course is described as covering general processes related to battery inspection, maintenance routines, and reconditioning methods for certain chemistries, including automotive batteries, deep cycle units, and smaller rechargeable cells. It functions as a compiled educational reference that outlines procedures and technical considerations in a structured format. In the broader landscape of sustainable home energy discussions, materials of this type represent one category of informational resources that examine battery reuse strategies from a procedural perspective. They exist alongside other educational materials addressing battery chemistry, system integration, and lifecycle management. Exploring reuse strategies for common rechargeable batteries involves examining the role these devices play within everyday household environments. In some homes, replacement remains the standard response to declining performance. In others, maintenance, repurposing, or structured reconditioning methods are considered within specific limits. Approaches vary depending on battery type, system integration, technical familiarity, and individual priorities. Not all rechargeable batteries are suitable for reuse beyond certain thresholds, and outcomes depend on chemical condition and design constraints. As sustainable home energy systems continue to evolve, conversations around battery lifecycle management are likely to remain part of broader resource efficiency discussions. Understanding the context in which reuse strategies emerge provides perspective on how households engage with rechargeable technologies. This content is presented for informational purposes only and does not provide instruction, recommendation, or technical guidance.